Hi, my name's Arpad. I'm going to talk today about, well, how your application state gets to the screen and how to get it performant or why it's not so performant. So this is actually like a follow-up talk to a talk I held earlier this year, and it took me a lot of time to actually get to do this talk because lately I've focused my Wednesday nights on improving my tricking skills instead of improving my JavaScript skills. So I'm a front-end engineer at PageStrip, and we are actually looking for Mac developers now. So if anyone wants to do Objective-C, please talk to me. And well, I used to be a regular speaker at ViennaJS, and yeah, I do have a lot of JavaScript experience. I worked with JavaScript for a lot of years, and I've also done a little bit of JavaScript engine development. And something I'm really focused on is performance. And I do rant a lot about the Java ecosystem, but please don't take those things too seriously. Well, the talk is basically focused on this. So today, all the modern games look fabulous, and they run really smoothly on 60 FPS, well, at least on halfway modern hardware. Well, actually, they do run on 90 FPS because of VR, because 60 FPS on VR would be not such a smooth experience. So the games actually run on 90 FPS now. And that's basically a budget of 10 milliseconds per frame. And the problem with JavaScript is, if you can read this here, this is like a Redux logger log, and it's actually, well, JavaScript is well over the budget, only for JavaScript, and there's rendering on top of this. So the simplified architecture of a modern JavaScript app is basically a set of transforms. So you have your state, your domain models, and you transform those to your views, to your DOM and your CSS, and this gets transformed into the pixels on your screen that you can actually see and interact with. And if you're interacting with this, you as a user trigger actions with the user interface and actually cause updates to this state tree or to your state. So let's start from the end. So how do the pixels actually get to the screen? And let's start from the very beginning, because this here is an example of OpenGL1, which was in '92, a really old graphics API. What you basically had to do back in the days was you had a function to set the color of your triangles, and then you had to start a triangle. You had to call functions to define every vertex of a triangle, and then you had to finish this triangle. This kind of reminds me of how Canvas 2D works. You have a global state where you have your stroke style or fill style, and then you have all those API functions to start a path, to move and create lines and arcs and whatever, and then you finish the path or your drawing by stroking or filling it. And what this is called is immediate mode graphics. And immediate mode graphics basically means that with every frame, you throw away everything you did and you start all over again. So you execute all these steps again and again and again, which, well, isn't that performant. And the thing is that drawing in the browsers actually is based around 2D graphics, the 2D graphics model and immediate mode graphics, which hasn't changed so much over the years. I mean, there are 2D graphics APIs which are not as immediate mode as, for example, Canvas 2D. So, for example, the platform 2D APIs can hold more objects into memory that you don't have to recreate on every frame. But there's still a lot of immediate mode drawing going on. And browsers actually do cheat a little bit because they group parts of your screen into layers, which are then just drawn into textures, and those textures are composited onto the screen. Here's, for example, a view of the Chrome dev tools, the layers panel, which you can actually enable in the options, which shows you a tree of layers. And the problem with this is that if you're doing 3D transforms or scaling and so on, especially WebKit and Blink-based browsers, they are just scaling up the texture. So you have blurry fonts and blurry images all over the place, which is not really that nice to have. And also Firefox has also some kind of problems. For example, this slideshow presentation, which actually runs in a browser, if you are running it in Firefox, you can see that the screen actually, the quality of the text changes when you are transitioning a slide or when the slide is fixed on the screen. So Firefox also has some internal optimization, so just draw into a texture and then translate the texture, which leads to visual artifacts, which are not really nice. And this, by the way, is also the paint profile in Chrome, which basically shows that you're having a lot of separate draw commands to draw text, draw rectangles, and so on and so on. Thing is, Firefox only does it when things are animated. So when you're animating something, if it has a fixed position, it's pixel perfect. Then you're moving it, it's animating, so Firefox changes the quality of the thing. And when it stops animating, then the quality changes again. So you really can see those changes of visual quality.
Chrome does it all the time.
Yes, Chrome does it all the time. So be aware and don't overuse layers in 3D transforms, because if you're doing it wrong, you get blurry text, which is not really that nice. Well, fast forward 24 years. So 2 slides ago, I showed you the API of OpenGL 1. Now we have something called Vulkan, which is like the really hyped successor to OpenGL, which has a very low-level access to the GPU. And well, I might not be that kind of an expert on low-level 3D graphics, but as far as I understand it, Vulkan is basically based around a concept called command buffers. So you can create command buffers on different threads, because the problem with OpenGL was it didn't have like multi-threaded state. So Vulkan fixed this by allowing you to create different command buffers in different texts. And those command buffers just are basically the rendering commands. Vulkan is more of a retained mode API than OpenGL is or was. And, well, did you see it? It actually stuttered there a little bit. So the thing that's currently happening in the browser world is something called web render, which started out as a research experiment inside Servo, which is a research browser engine headed by Mozilla. And what web render is basically retained mode drawing for the web. It renders web pages as if they were video games. Video games are highly interactive, and every frame in a video game is drawn separately, which is kind of contrary to what I said about immediate mode. But keep in mind, your GPU has up to 2,000 separate cores, which are highly optimized to do those kind of graphics. So actually using the GPU for them is a really, really good idea. And there are a few benchmarks and demos where a web render can easily achieve up to 600 FPS, depending, well, on the benchmark and on the hardware. This is one of those short examples showing you a few demos where current browsers really, really struggle with as low as 5 FPS, and in Servo and web render it runs really, really smoothly. And well, this is like a kind of short little trivia. I compiled Servo a few days ago just to try it out again. And it took me an hour to compile, which means I really do need new hardware. When you actually can do rendering really, really fast with up to 600 FPS, the bottleneck shifts one layer down. So we have the rendering. and now we have the DOM mutation. So this is a really nice video from Patrick Walton, which is one of the developers behind WebRender and Servo. And it's a really nice talk. You should watch it if you have time. And there are some key points he talks about. For example, that the bottleneck shifts down to actually CSS and restyling, which is basically setting your style properties, actually moving blocks around or changing the CSS transform of things becomes the bottleneck. And you can basically ignore those 2 points. This was like some assumptions I made. I'm not really sure if this is really the case, that actually passing those CSS strings is the problem, or basically the layouting or the CSS calculations of the browser engine itself. But there is, again, this notion of immediate mode rendering, because instead of just mutating an object and moving it somewhere else, you're actually completely throwing the state away and creating a new style state for it, which is expensive. And this was also announced yesterday. Mozilla is actually trying to integrate WebRender into Firefox with a new initiative called Quantum. This was announced yesterday, so go for it. The thing you can do to speed up this CSS processing, or to be faster and quicker to actually manipulate CSS properties, is something called typed CSS, which is currently in the draft state and it's heavily debated. And the CSS Houdini group is heading the effort. That's a group that's focused on giving CSS authors more of a lower level access to the drawing primitives of the actual browser. And this basically avoids all the CSS serialization and parsing of CSS value strings. But the API is still immutable. I'll come to this in a second. So the problem with JS is actually this. And this is a quote I found like a few months ago, which I believe it's really funny and can be applied to a lot of things. If you replace a few words here, it says the most amazing achievement of the JavaScript developers is its continuing cancellation of the steady and staggering gains made by the browser vendors. Okay. If you're looking more deeply into how all the really hyped JavaScript libraries work today, you find out, or you read a lot about of things. For example, this is also a really informative blog post about what makes React actually unique. And Andreas Stahls is saying that the virtual DOM allows us to convert mutable retained mode graphics API into an immutable functional immediate mode API. So the browser vendors are actually moving from a immediate mode 2D graphics API to be more of a retained mode API. And the JavaScript developers are actually doing the opposite thing, which, well, means that React is based around the concept that you're recreating your whole rendering tree, or your virtual DOM in React words. You're recreating your complete virtual DOM in the React render methods of your React components, which creates a lot of objects and so on and so on. And this has to be diffed against the real DOM in the browser, which is an expensive operation. And this is such an expensive operation that for React Native, the React engineers, this is also a really nice talk from one of the guys behind React Native. So the React engineers figured out that React isn't such a good fit for animating UIs because it's so slow. So they tried a lot of things, and I would really recommend you look into this presentation because it really shows the thought process and the evolution of how to make React faster for animations. And the key point here is they basically resorted to direct DOM manipulation. So instead of changing the state on React components and having the whole React component recreate the virtual DOM, they are completely sidestepping this issue and doing direct DOM manipulation. And if I read the React Native changelog correctly, they even moved the whole animated component to native code. So if I interpret it correctly, they even do like value tweening and value interpolation in native code and not in JavaScript. So the next thing is, so we have this view. Now we're going one step back again and looking at the state. And there's a lot of hype in recent times about immutable and also fractal architectures, and also functional immutable programming and so on. There's different issues with this, and one of the things I find is really hard to grasp as a developer is that if you are working with an immutable architecture, you basically have to treat your domain model, the state of your application as a database. So if you have highly nested models, and it doesn't even need to be highly nested. If you have like a list of to-do items, that's the basic example, like the to-do list is one of the basic examples of JavaScript frameworks today. If you add just one field, like the author or the owner of one of those to-do list items, then instead of a state tree, you'll get a graph, because one owner can have multiple to-do items assigned. So it's not a flat tree again. And so you actually have to do something like database normalization that you maybe know from university. This is the Redux docs for it. And it's really complex to do. It's really complex to do. Basically, the state becomes like this. You have more or less SQL tables. So you have content indexed by ID, publisher page, and font. That's what our application used to look like. And if you're going the immutable way, on every state change, you basically copy all your things. And I know this is a bad example, but I was actually too lazy to do it properly, so I just copied everything. But if you are doing immutable data, you do have to copy a lot of things. And inside your render function, it also gets messy because you have to, if you're using Redux, you have to connect every one of your components, or you have to just pass down your entities from parent to child all the time, which is really annoying. And yeah, Redux has this concept of selectors. Like I said, when you're using Redux, you're connecting all of your React components, and you're writing selectors, which take the immutable Redux store and your immutable Redux state and massage it into the objects your view, your React component expects. And what you're basically doing is writing an SQL join statement here. And depending on how exactly you're doing it, you're also creating a lot of new objects, which defeats the whole purpose of the should component update functionality of React, if you're familiar with this. What about Elm? Elm is also a strict functional programming language, which coined the phrase of the Elm architecture, which basically means that your child component state is completely wrapped in your parent component state. So it's what they call a fractal architecture, because the parent contains all the state of the child and so on and so on. So you can nest it as deeply as you want. But the problem is, due to immutable functional programming, you're recreating the whole parent chain if you are changing one of your state objects. So you also have to render everything from the parent up to the child that actually changed. And there were a few really, really nice talks on Monday and Tuesday. And unfortunately, I couldn't be there on Tuesday, but I think there was also a talk about Elm, right? Yep. And I would have really loved to look at this talk, but well, 2 weeks online. 2 weeks online, good, very good, very good. So I would actually love to hear from like a really proficient Elm developer how they deal with such problems. For example, this is actually a GitHub issue I created on the Elm guide, where I just explain the issue I had, which I explained to you right now. So if you don't have a simple tree in your data state, but actually have a graph, for example, if you add the owner of a to-do list item, then you have to do all this similar to SQL normalization, and you have to pass down either your entities down to all the children. And I think there has to be a better way of doing this. So I created an issue. So please come on, Elm community, explain to me how you can do it efficiently. And well, I was rejected, but I don't want to flame anyone. The basic conclusion of my talk is that the change of the JavaScript community gives me a lot of fatigue lately. And there's a lot of influence from the purely functional programming camp, for example, with the concepts of Redux, with Elm, and with all those immutable data kind of programming. But there's still unsolved problems, for example, with performance and also explaining those concepts to developers. For example, if I don't really get it how you normalize your data, how you make it efficient to render afterwards, then I bet a lot of other developers will not get it as well. And the basic key point is, remember, JavaScript sadly does not offer zero-cost abstractions. So if you're piling layers of abstractions onto one another, your users will feel it. And the browser vendors can speed up rendering how much they want. If you're doing 10 layers of abstraction in JavaScript, your users will still feel it. So just keep in mind. All right, that's basically my talk.
Thank you for watching this talk. Down below, you can find our channel, ViennaJS, where you can find a lot of different videos about front-end and back-end JavaScript. And feel free to subscribe.